1231 deals with it's something called a characteristic curves. And most solid state devices have this. And it's something that we teach in textbooks, but odds are you're not going to see it in the data sheet. But the information from the data sheet, you usually can develop these. So for a diode, so we have a vertical axis and we have a horizontal axis. This is reverse bias. And this is forward bias. And over here we'll start with very small increments, like I'm not going to use legal engineer notation because the sheet doesn't use it. Like this will be volts, and like 0.1, 0.2, 0.3, 0.4, 0.5, 0.6, 0.7, and it probably goes out further than this because 0.7, remember 0.7 is an approximation. We call it the second approximation, which means it's good enough for math, but it's not actually what's going on in real life, right? 0.08, 0.09. And what happens when we start forward biasing this, if we was to measure the current, as soon as you put a voltage across here, we have a little bit of current like this. And I'm sorry, this is I forward, and this is I reverse. And when it gets around 5/10, right around 6/10, it's going to start up. But it's not going to be vertical. It's going to be at a slight slant, which indicates that the voltage does change. The more current you put through it, the more voltage it drops. So I think for the 1N 4000 series, it says this could get all the way up to 1.1 volt at 1 amp, which is what it's rated at I think it's 25 degrees centigrade. I'd have to go back and look at that. This is what we call a diode's VI characteristic curve. Yes, VI characteristic curve, and that's what this is called. So on the on the horizontal axis, these are volts. Now over here on this side, it's going to really go up. Because this is the reverse characteristics. And this is so over here we're indicating what we call the breakover voltage. So the analogy I use is kind of like the tensile strength or the breaking strength of a board. So every board would have what they would rate it at, right? Which means, okay, if I put the board out, horizontally and started putting weight on the end, when would it break? That makes sense. And they're all going to break sooner or later. And you can tell right off the bat that's not good, right? So on this side, we'll come over here and we'd start over here. This would be leakage current. It's going to be a little more. And then somewhere along, depending on the rating, this is going to break over. And for a regular diode, this is bad. Because if you ever break it over in the reverse direction, then odds are a standard diode. Now, we're going to look at a diode next week that is designed to operate in this region over here, in the reverse breakover voltage. So what we're going to do in this lab is you're going to make or develop a VI characteristic curve for a 1N914. Got your test? So if we go, and so we got the data sheets available up online. So if we, I'm gonna pull them out of here because it's a little faster than me having to log in. So 1N914. This is a little old tiny diode. This is a small signal diode. You're not supposed to use this. Well, you can, as long as you don't exceed the characteristics. So we have the absolute maximum rating tables. This says, okay, if I don't exceed these, then I'm going to not be damaged. So the average breakover voltage for this is rated at 75 volts. In reverse voltage, so they're calling it. So a lot of these data sheets, guys, you gotta read the actual what we're talking about. So they don't even call this PIV. They don't call it RMM. But over here they call it RIN, RIV. But this right here is the giveaway. It's the working voltage. So as long as we keep this thing below 75 volts in the reverse bias direction, then that means this guy shouldn't have any problems. As soon as we exceed 75 volts, this guy could break over. It don't mean it will, but it could. And the analogy I use, it's like a tack gauge on a car, right? So if you go over your recommended tack, it don't mean your engine's gonna blow up, but it could for overspeed, right? So this guy here, let's see, duration, thermal characteristics, electrical characteristics. So the breakover voltage, 75 volts. Let's see, reverse current. So this is the leakage current. So at 20 volts, we'll get about 25 nanoamps at a temperature though. So it says 25 degrees centigrade. So we consider that on most data sheets, that's considered what we mean room temperature. So on a diode, if heat goes up, leakage current goes up. If it's ambient temperature, and ambient temperature is the temperature where it's mounted, right? You understand that? It's working in. So it might be 75 degrees outside, but you got this sucker in a cabinet, and it's 100 degrees in the cabinet. Well, that would be the temperature that we're looking at. And the forward voltage drop on this one can be anywhere between a minimum of 720 millivolts, but it could be all the way up to 1 volt at 100 milliamps. And then, of course, this would give us how fast it can switch. So this guy could actually reliably switch up to 1 megahertz. And then these are just currents through it in different situations. So that means when we get around 75 volts, we should, I didn't see at 75 volts, we should see this break over. Now the problem is that if we let this thing break over and we don't protect it, then this is going to cause problems. But we're going to protect this with a 1 mega ohm resistor, which some of y'all hadn't even seen before. What's the color code for 1 mega ohm? Y'all gonna start seeing those on tests, guys. What's the color code for 1 mega ohm? So the circuit that we have, and it's in the, let's just bring up the lab. So the circuits you're going to be hooking up is, so this is where you're going to draw your VI characteristic curve. You'll come up with the current, and then we'll come up with the voltage. No, this is current. We'll come up with the current, and then the voltage is set up for you. We're going to have to rearrange this. This guy here has a breakover voltage of 75 volts. I don't know where they came up with this chart. So at 15 volts, this guy wouldn't be doing nothing. We can't. So we're trying to see where it breaks over. Okay. So this is a circuit that you'll be hooking up. It's going to be variable. This is the symbol of a DC. This is not the symbol Originally, this was the symbol for a battery because that was the first DC source people figured out how to make. This is a symbol now of a DC voltage source. It could be a battery, it could be a battery, it could be a cell, it could be your rectifier out there on your car. So this is the symbol of a DC voltage source. If it's got an arrow through it, it means it's going to be variable. So you can't use any of the fixed power supplies on there. On the trainer, you'll be using, and we're going to be using this a lot this semester. So I'm going to see if I can, I might have to raise my camera, even though I had it all set up for this. And in my classes, I don't like you to use the fixed voltage sources anyway. So on the trainer, we have two voltage sources available to us. So we have some fixed voltage sources. These are done by fixed regulators. And like I said, we'll take one of these trainers apart and let you look at all the power supplies. These are fixed. These are fixed. So we have, no, this is for a function generator. So it's got a built-in function generator on it. So just because you see a black terminal does not mean it's a common. So this is a clock, which means it's a digital clock. So it's up and down and up and down. And this right here is actually a function generator where you can get different signals. The type of signals that you get would be determined by this. So we can get a sine wave. We can get what we call a triangle wave, and then we can get what we call a pulse waveform or square wave. It's not really. This is where you set your maximum frequency, what you can go up to, and then of course this is where you could course adjust the frequency. And this is where you would fine adjust the frequency. This right here is a plus 5 volts relative to this common terminal. So this is a big problem I have with this trainer. They label this guy here as ground, but if you measure between this terminal and the little small round one on your power supply, on your power cord, it is not grounded. So this is ungrounded. This has nothing to do with the transformer. So some of y'all tried to hook up to this. We establish our common up here on this transformer in our circuit. Okay. These are your variable power supplies right here. So we have a negative power supply. I think it's 0 to 15 volts. Or, well, most variable regulators, it's real hard to get them to go to 0. So this is around 2 to 15 or 17 volts. This is your positive relative to this common. So this is the power supply you're going to be using for this lab. You'll be going, this is going to be your positive on the lab. This is going to be your common. Not your ground, your common. Everybody understand the difference? Okay. Not this guy right here. Okay. This is where you're going to adjust your power supplies. So this is where you'll adjust your positive variable power supply. This is when we get to it. So later on, we'll actually be using this guy over here. But right now in these labs, we're just going to be using this guy right here. So your circuits will be wired not to any of these. They'll be wired to this guy right here. And then you'll adjust the voltage with these two guys with this guy right here. Yeah, okay. We'll see when we go to lab, right? So what you're going to do, of course, we're not going to do any of this up here. It doesn't make any sense to measure resistors. We know right now that these resistors are plus or minus 5%. If you measure them, it's not going to make that much difference in your math anyway. 1 mega ohm, you don't need one of those. That's me. That's for my circuit. And here you just need to record the forward and reverse voltage, not the resistance. We know most of our digital meters won't even measure a reverse resistance. It measures overload. So I need to correct that lab. But this is on the diode scale. So you just measure your forward and your reverse. Of course, the reverse should be overload, right? What you're going to do is you're going to set these voltage levels. You're going to take your meter and measure it across the diode. When you get 0.54 volts, you're going to measure the voltage drop across a 330 ohm resistor. You're going to use that to calculate your current. A lot of people think if they want current, they gotta break the circuit and put that current and put your ammeter in there. If you have a series resistor, guys, you don't have to do that. You just measure the voltage drop across your resistor, and what? I is equal to V over what? V over R. So that's what they say computed. That is not measured, that is computed. Are we okay? And then when you record that chart, you'll come over here and you should see your curve start here and then come over here and move up according to these currents that you measure. So depending on your currents that you measure, this will set up where you scale this thing. Does that make sense? Now on this side, we're probably going to go 30, 40, 60, and then come over this way a little bit, because we know this diode does not break over until we get about 75 volts on there. Okay. So this toggle right here I'm going to do, so notice this guy's reverse bias. We're protecting this with a 1 mega ohm resistor. So we're going to watch this real careful. We're going to measure across the 1 meg. We're going to use, let's see what I have mine set up for. So you need to mark yours out. We'll go 30, 60, and then wherever it breaks over at. So is it going to break over at 75 volts? Probably not. It's always got a safety margin built into it. But it'll probably be right around 100 volts. So what we're going to do is we're going to look across this resistor and we'll watch it change. It's going to change real slowly because what you're doing is you're looking at leakage current. Right? You understand that? And the voltage, so we calculate our reverse current or our leakage current by using V over R. So I'm going to go to 30 volts. We're going to measure the voltage drop across the diode. Then we're going to measure the voltage drop. This is wrong. We're going to measure the voltage drop across R. Oh, I'm sorry, this is right. We're going to measure the voltage drop across the diode, and then we're going to compute the current. So here's the voltage drop across the resistor. So we go 30, 60, and then whatever voltage it breaks over at. We're going to take this slow. So what I have up here, I have all these power supplies, and they only output. So I got all these power supplies up here. And if I want to increase voltage, what do we do with DC sources? So we can hook DC sources two different ways, and you see this all the time with batteries. If I want to increase the voltage or add the voltages, how do we hook the DC sources? Got two ways. We can hook them parallel, we can hook them series. You learned this in DC. So we want these power supplies to add. So how do we hook them? Series or parallel? Series, good. So if we want DC sources, if we want to increase the current, and you see this all the time in batteries, where sometimes they hook them in series, sometimes they hook them in parallel. Parallel is to increase the current, series is to increase the voltage. So I have 1, 2, 3, 4, 5, 6, 7. I'm not going to need all these. I don't know why I got that many. And we've got them hooked in series. And this is any DC source, guys, even if it's electronic. So we got all these, and they're all variable, and we just got them hooked in series. Oops, I don't want to draw that many. Now, used to this symbol, the symbol when it first came out with batteries. In fact, with these little old double A's, these little double A's and triple A's and C's and D's, these are technically not batteries. These are actually what we call a cell, or should be called a cell. But the problem is when you had car batteries and then you had cells, so the average person got confused. So we call all these things batteries, even though a battery means more than one. So what we used to do, the symbol was each one of these represented a cell. 1, 2, 3, 4, 5. So your car battery should have been drawn like that because it's got 6 cells in it. They're hooked in series. Each one of them develops 2 volts apiece. They're hooked in series, right? You'll understand that. And they're also hooked in parallel. So basically what you got in your car battery is you got a cell, and right next to it you got another one, and right next to it you got another one. And then they come up here and they got all these connected together. If you ever took a battery apart, you could tell that. And then they'll take this and run it into another group of cells. So they're hooking them in parallel to increase the what? Current, parallel current, series voltage. So when we say we got 6 cells in there, that's not exactly true. So you got a bunch of cells. So if you ever looked at the plates in there, it's got a bunch of plates, then it's got a bar across the top of it, so that's in parallel, and then you got it running to the next set of cells. So how much current you get out of that thing would depend on how many cells they can hook in series, right? And how much voltage you get out would be how much they could put in parallel. How much current you get out of it would be how many of these things you could get in parallel, and how much voltage would be how much you can get. And this is why usually the bigger the battery, the more current you can get out of it, even though you've only got what? 6 cells. But over time, this became known as so when you get into your power supplies, it basically makes no difference on how many cells you put in there, because these electronic power supplies are not made out of cells anyway. But this symbol came up through batteries, or cells, I should say. So what we're doing is we're taking a bunch of these things and we're hooking them in series. And then I've got one, and they're all what? If we've got a line coming through it and you see an arrow, what does that mean? They're variable, right? So here I've got 6 drawn, but I got 5 drawn. So actually I got it hooked up like this. No, that's not even true. So I've got 12 of these. So the trainer is set up like this. So we got this power supply right here, and then we come over here, and we got this power supply right here. Then we have a terminal right here. That's called common. Well, they call it ground, but it's common. And then over here, we have this terminal right here. And it is, oh no, this power supply is right. So it is labeled common. And then we have a terminal right here. So this is your variable plus supply. This is your variable minus supply. So what I'm not doing is I'm not using the common. So we should get about 15 volts right here, 15 volts right here. They're in series, so I'm not using this. So I'm bringing it in here, and then I'm coming out here, and then I'm going to the next one. So that means each power supply should give me around 30 volts. And I've got 6 of them. So what should we get? Should be able to get around 180 volts out of these things, right? So when you look at the setup, and yes, we can hook these in series. They're just DC sources. So if you look at my setup, so you got car batteries out there. You need 24 volts. So you got a 24 volt golf cart. 24 volt batteries are very, very expensive. What can you do? You can get 2 12 volt batteries and do what? Connect them in series. If you need more current, so you go down to the battery man down on 15th Street in Bessemer. never bought a battery from them, but I've taken batteries down there. So here's my here's my plus. So we'll start on the minus side. So here's my minus. Okay. Okay. And so if you notice, I go from one to the other, to one to the other, from one to the other, from one to the other. So these are all hooked in series. Oh, sorry. So I come from this one. So here's my plus on this power supply. Then this yellow one goes up to the plus on this one. Then I take the yellow one to the plus, the yellow one to the plus, the yellow one to the plus, the yellow one to the plus. And so this right here would be my minus. So we have all these just hooked in series. No, don't look at the cords. Look at these guys right here. I've only got so many cords to deal with. So I did use a plus right. I did use a red right here for the plus, and I did use a black right here for the plus. And between them, I used what I had. Okay. So what we're saying is I take this plus right here, then I take this minus, and it jumps up to the plus on that one. I take this minus, and I jump it to the plus on this one, and I just hook them in series. So plus to minus, plus minus. So yeah, that's a good point. I'm glad you brought that up. No, the bag only comes with so many minus, pluses, and minus, and so many yellow ones. So I just made sure I ended up on my minus. I ended up with a black, and on my overall plus, I ended up with a red. So right now I've got 17 volts, but you can see I can come up on any one of these. So this is measuring the voltage drop across the circuit. And so see, I can turn this one, or I can turn this one. That soldering iron is hot, by the way. So we should get up to about 100, be able to get about 120 volts. So so these guys, each one of them puts about 2 volts out. So these variable power supplies, it's almost impossible to get 0 volts out of them. No, this is not an ohmmeter. This is a voltmeter. So I'm measuring the volts out of the entire string. It jumps it up or down. This is for the negative power supply. This is for the positive power supply. So this lines up, but it don't make any difference. I've got the negative and the positives hooked in series. Please don't be texting on your phone or doing something like that while I'm up here lecturing. That's not nice. So if I was to draw the schematic, then the way it's connected up is colors. So the way the trainer's wired, it has a positive supply, then it has a negative supply. This is connected together, and then this comes out, and they call this common, which is true. So this power supply is true. That's what it is. It's not grounded, it's a common. We do have a ground on the back. It's a green terminal on the back that I could run a wire around to the blacks and make this power supply grounded. But right now it's isolated. Now you note, and over here we got a terminal here that's black, and it's labeled minus. It's labeled minus 1.5 volts through 15 volts at 1 amp. Then this guy comes over here, and this is plus 1.5 volts to 50. So what I'm doing is I'm coming over here. So I'm coming over here. This is coming into one side of my circuit. Then instead of using the common, I'm coming over here. And then I'm hooking it up to the next power supply. Instead of using the common, I'm coming over here and hooking it up to the next two power supplies. So each one of these power supplies actually has two variable supplies in it, just like your trainer. So that means if I can get 15 volts out of this one and I can get 15 volts out of this one, what can I get across the two? They're in series. 30 volts. Then these are in series, so that's 30 volts. And these are in series, that's 30 volts. Well, I have 6 of these things. So that means I could get up to 180 volts. More than that, because that's what it's rated at. Very seldom do you get these variable power supplies that don't actually put out more than what they're rated at. And they're all variable. So no matter which one I turn, in the series string, my output voltage is going to go up because they're hooked in series. So what we're going to do, so I'm going to discard this, go back to my camera. Okay. So and this is my circuit. Can't hardly see it because I got so many meters hooked up to it. Here's the diode. Now I've only got 17 volts, so it's okay for me to touch. It's got a little black ring across it, so this is the cathode. The cathode is going toward my positive. Here's my 1 mega ohm resistor, which nobody told me the color code on. Black, right? Brown, black, and I need 5 zeros. So that's green. And then these are the commons for all of my meters and my power supplies. So I got to be real careful on that because it wants to jerk out. The resistor wants to jerk out real easy. So this is my circuit. So what we're going to do is we're going to come up here, and in your lab book you need to go ahead and make this correction where we're going to go across the resistor. We're going to go 30 volts, we're going to go 60 volts, and then whatever determines where it breaks over. And what we're looking at is we're looking for the reversed current to make a real fast change. So first of all we'll be looking at the fractions, and then all of a sudden you'll see the main units start changing. And as soon as those start changing fast, they're going to change slow, but as soon as they start advancing real fast, that means we've hit the curve. So let me see if I can get this meter in here without messing up stuff. Okay, so right now I've got 17 volts across. This is not our first measurement, but already we have leakage current. Already. So this is the meter on the right. This is measuring the voltage drop across my resistor. The meter on the left is measuring the voltage drop applied to the circuit. The one on the right is the voltage drop across, and it's on millivolts, by the way. So this is 5.2 millivolts that we're looking at right there. Okay. So this is on the 400 volt scale. So this guy right here is measuring volts. This is millivolts. So right now we're looking at a leakage current. So right now we would say 5.2 milli divided by 1 mega ohm, and that would give us the current. So what leakage current do we have right now? We're not going to record this. That's 1 meg. So we're probably down in at least the picoamps, right? But there is a path. We have a voltage. We have a path. And that's what we call leakage current. And so what I'm going to do, this is going to be one of your questions, is I'm going to come over here. I got a soldering iron. I'm going to go ahead and do it now. So what should happen to the leakage current when I heat this thing up? Is it going to go up or is it going to go down? It's going to go up. All right. So watch it. So if that voltage drop goes up on the right meter, it means that my leakage current is going up. And by the way, we use this feature. We use this feature of a semiconductor as a temperature sensor. We call them thermistors. So, and what happens, so this is free spray, by the way. If you get this stuff, don't spray it on you because it'll give you frostburn. We use this a lot to try to troubleshoot. Sometimes in electronics, things get hot, and when you cool them down, they work right. And we do that sometimes to find bad parts. So I'm going to come up here and spray it. And you see the leakage current did what? It did a nosedive. So that means this leakage current is controlled by temperature. We've always got it. But if temperature goes up, leakage current goes up. If temperature goes down, leakage current goes down. So this is why one of the reasons, if you let the leakage current get out of whack, though, you're going to cause problems. Because this thing's dropping a lot of voltage, and anytime you have current and you have voltage, you have watts, right? You understand that? So this is what usually damages it. So we're going to start increasing our voltage. So we're looking at this meter right here. And notice right off the bat, when I start turning up the voltage, the leakage current starts going up. But the only thing that's moving right now is the fraction. Of course, eventually, but what we're looking for is the top one to start changing about as fast as the fraction. So that's 32 volts I have across that thing. Still, we're okay. So, I'm sorry. This is 30 volts right here. So that's one of your measurements. So y'all need to go ahead and write the voltage drop across the diode down. Across the resistor. So that's the voltage drop across the 1 meg, and then we can use that to calculate our current. So we're going to do 30, and then we're going to go up to 60, but we're going to do it real slow so y'all can see when it breaks over. Or not real slow, we're going to do it slow. Well, what we're trying to do is the voltages are given, so instead of using the ones they do, I knew the diode never breaks over, so that's why we're going 30, 60, and then we're not going to do 90, we're going to go until it breaks over. So what we're doing is we're trying to figure out where it actually breaks over at. So the two things where it breaks over is, of course, the voltage drop that we put across it, and then the current that we put through it. So what's 6.5 divided by 1 million? So this is our computed current. Y'all got a calculator? I don't. Well, I do have a calculator. 1 million. We're protecting this thing with a 1 meg ohm resistor. So if I had a 100 ohm resistor out there, as soon as this thing broke over, this diode would be gone. But what we're doing is we're using that 1 meg ohm resistor. First, it makes it easy to calculate current. So once you figure this first one, guys, you probably don't have to do the math anymore. So I come over here and I say, okay, 6.4 divided by 1 million. So I come up here and I've got I've got 6.4 microamps. Is that what you got? So now I know every one of these answers are going to be in microamps. 6.4. So if I measure 10, that's going to be 10 microamps because we got that. We know that 1 meg ohm resistor. Is that what y'all got? Yeah, that's milli. I'm sorry. No, that's way down there. You're right. So see, you caught me on that one. I was just making sure y'all was paying attention. Yeah, it's down in the nanoamps, so that's divided by 1 million. Yeah, 6.5 nanoamps. Or 6.4 nanoamps, but that's okay. Okay, so you know these so nanoamps, everybody okay? So you know these measurements now are going to be in nanoamps. You don't need to so I'm going to, instead of saying 6.5 milli, I'm going to say 6.5 nano. Is it nano? Everybody got that? Everybody okay? Yes? It's a milli. So what we're doing, so you did what I did. It's not 6.5. It's 6.5 times 10 to the minus third divided by 1 million. 6.5. Yeah, so it's point 0.0065, right? Divided by 1 million equals that. So 6.5 nanoamps. So now we don't have to do the math anymore. I know all I got to do is read this meter and call it nanoamps, right? Does that make sense? So we don't have to do the math anymore. So now we'll go up to 60 volts, and we'll do that fairly slowly so we can see when it starts changing. So notice the fraction is still changing, and we still have to move it pretty far for this guy right here to change. Something's going on there. Oops. So there's 60 volts. So we got 9.1 nanoamps. Are we okay? Still moving slowly. What we're doing is we're going to start looking for, this major division to change as fast as this division right here is changing. That indicates breakover. That's exactly right. Whatever voltage that pops up on here when this guy here starts advancing real fast. That'll be our highest measurement. Break it over now. .1 milli, not 9.1. And that's why I punched it up. That's why I put it up here. That's why I did it in longhand. So it's not 9.1. It's 0.0091, right? Yeah, but what we were talking about is once I figured out that first one, then all I have to do now is call this nanoamps, right? You understand that? Don't worry about milli, because every time you come up, and that's what's nice about K's. That's what's nice about resistors that moves in tens. Because once you calculate that first one, then you can read from then on. You can read that in whatever unit we're in, right? Okay, so 76 volts. Yeah, sorry. So instead of getting down there, I'm gonna go up and turn this one. Looks like right about there. You'll see. You'll see. So we come up here, turn it real slow, and then all of a sudden the top digit starts to change. See how fast it's changing now? Right about there. Yeah. So it looks like it broke over right around 95 volts. Huh? Yeah. Right around 95 volts. Right. Yeah. So right around 95. So see, it was rated at 75, but it broke over around 95. Yeah, so we'll call that 95. And let me bring it back up. 17 nanoamps. And of course, what we're supposed to do now is at breakover, we're supposed to come up here and heat it up, but we already know what's going to happen. Yeah. So leakage current increases. And of course, we know when we cool it down. I don't want to get it too hot, because if I get it too hot, it's made out of glass, and if I cool it down too fast, what would it do? Shatter, right? See, look, it dropped down to, now that's freezing. It dropped down to less than what it was before we broke it over. So why are we damaging it? Well, we're watching the voltage, we're watching the current really well, and we're protecting this with a 1 mega ohm resistor. And you don't see many 1 mega ohm resistors. We used to do it with a 10, but it gave us a little problem because it gave us invalid voltage measurements. And the problem people don't understand is that when you put a meter in parallel, it acts like a resistor in parallel when you're measuring voltage. So when you do the when you did the meter certification, all y'all did the meter certification, one thing you did was measure the resistance of the voltmeter, and it measured around 11 mega ohms. We usually assume it's around, for your new meters, it's usually around 10 mega ohm. So what was happening is we were coming over here and we was using a 10 mega ohm resistor because we really wanted to protect our resistor. But what it was doing is it was giving us erroneous readings, because what was happening is we was coming over here and we had our diode, and then of course I'm just going to draw this as one power supply. And then what we were doing is we was coming over here and we had a 10 mega ohm resistor. And then we was coming over here and we was hooking our meter in parallel, and it had 1 mega ohm. So you got to remember this, guys. When you hook your meter across something, it's like putting a 10 mega ohm or 11 mega ohm resistor in parallel. So what was happening, instead of being 10 mega ohm, it was 5 mega ohm, and it made our math wrong, right? So if you go in tens, it makes your math real easy. But so now we're down to one meg, and we called it a 10-to-1 ratio. So if you put something in parallel with, and it's got 10 times more resistance than what you measure, we can ignore the meter. We had a guy working at US Steel, and he wanted to measure the voltage out of a mag amp. This is what we used to do before we had operational amplifiers and everything. And it has an extremely high impedance. And he went over there and he put his voltmeter across it and shut down the line just like that. Because he didn't take into consideration he would load that mag amp down. He would change the voltage out. All the electronics said, hey, something's going on. The speed's not right. And it shut the whole line down in a heartbeat. But Dennis, he was in the big old line. It was pretty neat. So the big old control houses, they had a door. They had a section on it. It had a door on it. And then the door that came into it was right here. Well, Dennis was back in here measuring that mag amp. He shut the whole line down, and we called them blue hats. These were all the bosses and everything. They come running into there, and Dennis was back in the little slot back there, and they didn't know he was back there, and Dennis didn't say anything. So they came back in and reset the line, come back up, and Dennis waited till everybody came out, and then he snuck out. Nobody knew he did it. So true story. Dennis was an instructor. He's smart. Dennis is as smart as a whip. But he taught here for us a while. He finally moved up the ranks out at US Steel, and so don't take for granted. So that's something you got to think about, that voltmeter. You're not putting a infinite resistance in parallel with something. You're putting about 10 megohms in parallel with something. Now, if you're reading across, like we've got, we're reading across a 1K ohm resistor, and you're putting 10 megohms across that means nothing. And we call it the 10-to-1 ratio. So what that means, if what you're putting in parallel, it has 10 times more resistance than what you're trying to measure, we just ignore it. It's not going to cause any problems. So yeah, that was a true story. So what was happening is we was dividing by 5. We was dividing by 10 instead of dividing by 5. That wasn't even accurate too, because that's an approximation. So the snap-on meter says about 10 meg, but when you actually measure it, it's up around 11. So I don't know, y'all did that. I don't know if y'all remember that or not, but you put it on volts. You got 2 meters. You put it on volts, and you measured the actual resistance of the meter. All right, guys, that's that section of the lab. So when you get through with the lab you're working on, you need to drop back to 31 and do the portion that you were supposed to do. So we'll just figure out how to do that. So before we do that, let's go ahead and figure out this scale. Now I can't do this side. So what you'll do is you'll take the maximum current that you read, and you'll try to set it up in even scales. So you got to have at least the maximum up here somewhere, right? You understand? And then of course over here we can do that. So what was our maximum current? 17 nanoamps. So we're going to mark this off. So let me cut and paste. Oops, that's the same thing I put in here before. Hold on. The cut and paste is different on this computer than on any other computer I've dealt with. What's it doing? Oh, I know what I'm doing. Duh. Let's go duh together. So we're going to mark these off. So what are we going to go? So we got 1, 2, 3, 4, 5, 6, 7, 8. And we did what? We did 30. We did 60. And then this right here would be 90. It's going to look like it's going to work out okay, guys. So this right here would be 115, right? So that would be our vote. Huh? Yeah, 115. Yeah, that's the one right on the end. And then our currents on the reverse side, we've only got 2 to work with. So what was the maximum we got out of it? Okay. So if we made this 10 nano and we made this 20 nano, then we'd start right here. And what do we have? What do we have at 30 volts? Okay, so we'd come down here and put this right about here, right? And what do we have at 60? What do we have at 60? Okay, so that would be right on top of the line. And then what do we have at 90? So that would be down here. And then where do we have at 100 and what was it? Did we go 90? Did we do 90? Okay, so that would probably be it. And then, of course, then it would start doing this. So this is this side of the chart for y'all. And then, of course, you'll do the other side. But what you're going to do is you're going to use the positive variable supply. So you're going to use that little terminal that says it says positive V. And then, of course, you're not going to use the negative. You're going to use the one called common. Do they call it common? No, they call it ground. I'm not going. I will not call it ground. The trainer calls it ground. How do they abbreviate that? G and D. That is not ground, and it's got a couple of y'all messed up. So your circuit is going to come over here, and it's going to come over here. And let me look at the circuit first. I think the I just don't remember where the diode's at. Yeah, I know it's in series, but I don't know which is it. The resistor comes first. Okay. Yeah, because you could hook it up either way. It's just this would be a little easy. No, this is 32-2 is I hooked up, and you can see. Yeah, well, that's not the one y'all gonna hook up. You're gonna hook up 31-1. You're gonna forward bias it. So what you're doing is you're working on the forward bias section of the graph. We did the reverse bias, and you can see why we did that as a class. Why? Because my power supply has got up to 90 volts, right? Which is well above the lethal level. So the lethal level is actually the 70E standard specifies lethal. Anything above 50 volts has enough potential to push enough current through your body to kill you. So on the positive, the resistor comes first. So we'd come out. I'm using the wrong supply, guys. Don't pay any attention to this. Sorry. So we're using the positive supply. Nobody called me on that one. You say, well, you're the teacher. You should have known, right? But I did that on purpose so y'all could see if anybody found that. No, I'm wrong. So we're using the positive power supply. So that means the long one points there. It's variable. So your circuit's going to come out, and you're going to put the what? 300 ohm resistor. You're going to put the 1N914 with the cathode pointing toward the positive, and then this right here will come back and go to your common. So that'll be your circuit. Everybody okay on the trainer now, right? So any questions on this? And then, of course, like I said, you'll take your maximum current, which will probably be at 0.8 of a volt. So you're going to make measurements. So one of your meters, one meter is going to be, you have to move your meter. So 1 meter is we're going to measure across. So first of all, we're going to use our meter to measure across the diode. I can't draw on this, Rich. I'm going to use my meter to measure across the diode. We'll start off with 4.5 volts. We got a problem. So that circuit won't work. Can anybody tell me why? No, we're okay. We're okay. I don't know. I don't know if we can adjust down to 0.45 volts or not. That might be the problem across the diode when it's forward biased. So it's going to be, no, we can't do that, guys, because when it's forward biased, if we're below 0.7 of a volt, this guy right here is not going to conduct. Our trainer puts out about 2 volts. So how am I going to get 0.5 volts when the minimum my trainer puts out is 2 volts? So we're going to have to modify our circuit. Anybody give me any ideas? So I got a power supply. Let's say I got a 5 volt power supply. That's all it is, 5 volt power supply, and I want to get 1 volt. What would I use? Couldn't just use a resistor. Go ahead. Well, no. So this diode does not start conducting until it gets 0.7. Okay. And that's what we want to see. So we want to get 0.54 volts across the diode. But the problem I've got is that my trainer. Yeah, so what I'm saying is the problem is not a bigger resistor. A bigger resistor would just change my calculation. So basically we're starting off with this right here until we get up to 0.7 of a volt. Once we get up to 0.7 of a volt, the switch closes. So this could be a mega ohm resistor right there. That's not going to change my problem. My problem is somehow I've got to get less than 2 volts out of my trainer. We got to add one component. We could come up and do this, but then we would constantly be changing resistors out. So I could set up a voltage divider. But I don't need a fixed voltage divider. I need a variable voltage divider. What component do we have that's a variable voltage divider? So nobody in this class knows. That's disturbing. Huh? It's something y'all have already learned. Y'all hadn't learned, not in this class. It's something you should already know from previous classes. So what do we use this thing right here for? Of course, what's this? What's that the symbol for? A what? Well, we have, this is what we call a rheostat. So we use a rheostat to control the current. In fact, you very seldom see rheostats because this next component, we can make it serve two functions. We can make it work as a rheostat, or we can use it. So this is the guy I'm looking at. So we'll have to add one of these. And what's that? Potentiometer, right? A potentiometer is a variable voltage divider. So what I can do, we'll have to find some 10K pots, guys. I should have had them ready. So if I come over here with a potentiometer, and I come up here and put plus 10 volts at the top, and then I have my potentiometer right here, and then this goes to my common. If I adjust this up to right there, I'll get 10 volts out on the wiper. If I adjust it down to here, I'll get 0 volts at the wiper. If I put it in the middle, I get 5 volts. If I put it anywhere. So what we can do with this is a variable voltage divider, which means we put a voltage on top, and then I can divide that down in any ratio between the maximum voltage all the way down to 0. So that means our circuit is going to look like this. I'm drawing this backwards, guys. And so here's my common. I'm not going to draw the negative supply. I'm going to come over here, and I'm going to adjust this to something. More voltage than I need. So I think the maximum we need would probably be around plus 5 volts. Then what I'm going to do is I'm going to come down here and connect this to a 10K pot. Then I'm going to take the output of the potentiometer and I'm going to hook it up to my 330 ohm resistor. Then I'm going to come over here and my diode is going to be forward biased, right? So or common. Yeah, and out there in the real world, you can odds are you're gonna call this a ground, but I really want you to understand the difference between a ground and a common. So if I use this trainer right here, at both these trainers, the power supplies are ungrounded. So in these trainers, that little lead, that little black one, they say ground is not ground, it's a common. If it was a ground, you could take an ohm meter, put it in that black one that says ground. You could unplug this thing. You could hook it up to the little ground terminal on there, and you'd measure 0 ohms. And Lee did that the other day, by the way. And the transformer is even isolated from that common. So when you're doing your power supplies, the common is your common. It has nothing to do with that common on there. And that's what happens when people do this lab, is they'll hook up their common over there to the common on the trainer, and then all their measurements are wrong. So on that transformer, your circuit establishes your common. The way you wire it establishes your common. Now, as soon as you hook that scope probe up, you establish a ground. So that little old black lead on your scope probe is ground. And that's one reason why you can't move the black inside the circuit. Y'all hadn't? That's supposed to be one of the labs in D.C. And probably that at that point, that was probably one that was done virtually, unfortunately. Yeah. Well, it's got 3 leads. It's obvious. We're going to use a rotary pot, which is like this. There's linear pots. It's got 3 leads coming out of it. 1, 2, 3. Normally, and guys, I should know this. So this might be 1. The wiper is always 2, and this would be 3. Now, the difference between 1 and 3 would be which direction the pot turns to make the voltage goes out. So if you use 1 to your power supply, it might be clockwise. And if you don't like that, you just swap what you call 1 and 3. So if you want your voltage to go up when you turn it clockwise and it goes down, then swap 1 and 3. And I should know that, guys, but I don't. But this is 2 right here. That's 2. So that's the one that's going to connect to your circuit. So this would go, maybe this would go back to my source. So notice this does not connect to your circuit. What connects to your circuit is 2 on the potentiometer. And then, of course, our common. And remember, this common does exist. So that means I'm going to have a wire running from here, because this is the common of the power supply. So you're going to have that wire running right there. But look how much cleaner it is if I was to come up here and just come over here and put that symbol up here. That's what I should have done, so y'all can see the whole circuit. So this right here has that symbol right there. So what I'm doing is I'm taking a symbol that represents the common. But you got to understand, you have to hook that wire up. That represents a wire. I've heard this I don't know how many times, especially in D.C. Well, I thought that was inside the trainer. And here you got that. Some of y'all's done that in this class. So you got a vertical line right here. You got a resistor coming up here. And you don't have anything connected in the vertical line. Well, that resistor's just there. Y'all understand that. And that's even happened in this class. And I kind of understand, guys, because I know y'all didn't get very much hands-on labs in D.C. And so we're trying to make this up, and this is something you got to understand about a circuit. The number 2 lead. It's not a position. Technically, if you could adjust this thing accurately enough, you have an infinite number of voltages you can get off this thing. But it's going to be impossible. And you'll see that. And the bigger the pot it is, the harder it is to adjust. Huh? Let me pause my lecture. What it means is, if it says it's a 10K pot, that means if you measured between 1 and 3, it would measure approximately 10K. For that one you read. So we got some 100K pots in there. We got some 1K pots in there. Approximately 10K, because these things usually have a tolerance around 10%. What are resistors rated in? What 3 things is a resistor rated in? What 3 things? Next test. What 3 things are a resistor rated in? Watts, tolerance, and ohms. They are not rated in volts. So what you mean, so if I've got a 100K pod and it's rated at 10 watts, if I put enough current through there to make it get 10K, then make it do the watts, it's going to burn up. So pots, all resistors, where they're variable resistors. By the way, what's nice about a pot? So this is about done away with rheostats. So I've got 2 devices that would cost about the same, but what I can do with a pot, what I can do with a potentiometer, is I can take my wiper and connect it to one side, and it acts like a rheostat. So that means we can have a potentiometer that I can wire to act like a rheostat, or I can use it as a potentiometer. So it's almost impossible to find rheostats anymore because of this feature right here. So if I can wire something to act like this and they cost about the same, why would I as a company produce 2 different things? So this is a pot wired as a rheostat. If I say R-H-O-S-T-A-T-E, I think, is rheostat. So that's wired as a rheostat. So you'll see this all the time. So we usually use a rheostat to control a current, and we use a potentiometer to control a voltage. That's their main uses in life. So we're not changing the resistance between 1 and 3. We're changing the resistance between 1 and 2. So if the resistance between 1 or 2 is going up, then the resistance between 1 and 2 is going up, then the resistance between 2 and 3 is going down. But if you use a measure between 1 and 2, and then jump down and add them together, it should come up to be about 10K. Now notice I said about 10K. These guys, these are quarter watt potentiometers. So we don't need to get too much current flow through them. And these are 10K pots. So all you have to do once you get it wired up is now don't use this to convert. So set that at 5 volts. And I want you to use the variable. Don't use the 5 volts. I want you to get used to using that. Once you set that to 5 volts with your meter, you're through with adjusting the potential. Then you're going to adjust your voltage with the potentiometer. And now we can set it to anything between 5 volts. We'll never get it up to 5 volts. So what we're going to do is, first of all, you're going to take it and measure it across your diode. And now we can set it at 0.5. We can set it at 0.5 volts or 550 millivolts. And we're going to measure across this right here, and we should measure approximately 0 volts because the diode is not biased yet, right? We got to get up to around 0.7 of a volt. Then we'll go to the next one, and all of a sudden you'll see there'll be a voltage drop across 330. That means the diode is forward biased and it starts working. I mean, it's actually, now the switch is closed, right? You understand that? And then we should see a voltage drop. We're going to take it all the way up to 800 millivolts. And we're going to get our current, not by measuring current. We're going to calculate our current, and how are we going to do that? Through our diode, not through the pot. We're going to use the pot to set the voltage. How are we going to calculate our current? Not times. Yeah, so we're going to measure the voltage drop. So we're going to say I is equal to V over R. So we're going to say I is equal to whatever voltage we measure across that divided by 330 ohms. And we're not going to measure the 330 ohms because we know everything's an approximation in here anyway, right? You understand that? So this is a circuit. Now what I want you to do is go ahead and get through with your unregulated power supplies and then come back to this, and then I'll look for knobs. Oh, these aren't too bad. They turn pretty easy. Yeah, so we don't really need knobs on these. Some of them you can't turn. So if I was to take a meter right now, I've got it turned all the way to one side. Then if I measure between 2 and that side, it would measure about 0 ohms, and this side right here would measure about 10K. And so the sum of the voltage drops, the sums of the resistance between 2 and the two sides would always add up to be around 10K. Anybody put their own meter on here to see what it actually measures? Between 1 and 3. What you got, Lee? What you got between 1 and 3? You measuring it? You're not talking. It does say 10K, right? All right, guys, let's go lab.